start the third module. One nimisha. Good morning, students. You have already completed two modules, module 1 and module 2. And today I'm going to start module 3. In module 3, you're going to study about fault-based testing and structural testing. And the chapters from textbook 2 are 12 and 16. And 2 chapters from textbook 1. So first I'll start with the fault-based testing. Then I'll start with the structural testing. In the structural testing, you're going to study about the path testing. So path testing, which is included in chapter 12, and very less portion is there in chapter 12. And hence you have to study the path testing in detail. That includes DD paths, test coverage metrics, basic path testing, guidelines and observations. These things you are going to study from chapter 9 of textbook 1. Clear? Understood? So here in third module you are going to study about the fault based and structural based testing. For fault based testing, chapter 16 you have to study from the textbook 2, and for the structural testing you have to study the chapter 12 from the textbook 2 as well as chapter 9 and 10 from textbook 1. Is it clear now? Understood? Okay, so what are the chapters you have to study? So first I'll cover the fault based testing of chapter 16 from textbook 2, and after that I'm going to start the structural testing, that is chapter 12 from textbook 2, and path testing is also included in structural testing, but very little bit is covered in the chapter 12, and hence I'm going to explain in detail about the path testing and data flow testing from chapter 9 and 10 of textbook 1. Is it clear now? Okay, so I'll start with the fault based testing. So here you are going to study about what is a fault based testing. And next you are going to study about what are mutations, then what is the mutation analysis, and next you are going to study about the fault-based adequacy criteria, and then you are going to study about variations of mutation analysis. So these topics you are going to study from the fault-based testing. So this is the 6th chapter from textbook 2. Okay. So we'll start with the fault-based testing. So why do we require the fault-based testing? And you have already studied in the first chapter that what are the faults or what are the errors. A definition is also given, and I also explained the what the examples for the faults or errors in the first chapter itself, that is in the module 1, right? So no need to explain what are the faults or errors once again, right? So here we are using those faults to test the developed program or the developed system. Okay, so fault based testing. So a model of potential program faults is a valuable information for evaluating and designing the test suites. So in order to test the developed system or the program, we need the test suites or the test cases, right? Then to evaluate these test cases or the test suites, we need the program with the faults. Okay, so a potential program faults is the valuable source of information. Okay, a program with the faults is a valuable information for evaluating and designing the test suites. Understood? So to design the test suites or to evaluate the developed system or the program, we need the faults. Hence a program with a fault is the valuable source of information for evaluating and designing the test suites. So then how we need to include the faults, or how we need to develop the program with faults? So we need some fault knowledge, and that is commonly used in functional and structural testing. Okay, so some fault knowledge we require for the fault based testing, and it is commonly used in the functional and structural testing. Next, also, whenever we are using the fault-based testing, we are using the fault model. Okay, so for the fault-based testing, we are going to use the fault model, and that fault model is directly used to guess the potential faults in a program under the test. Okay, so in order to test the program or the developed system, we are going to use the fault based testing model. Okay, and this fault based testing model is directly used to guess the potential faults in a program that is under test. Understood? Clear? So in a fault based testing, we are going to make use of the fault model, and this fault model is directly employed or directly used on the program on test in order to guess the potential faults which exist in that program. Understood? So basically, what is fault based testing? We'll make use of the faults in order to test the developed program or the developed system. Okay. So, for example, if you consider the engineers, they study the failures to understand how to prevent similar failures in the future. For example, if you consider a simple computer engineer or a simple software engineer, so what he is going to do? He is going to study the failures. Suppose, consider an example that you have developed one system. Okay, then that system needs to be tested. Okay, when the system is tested, it results in failures. Okay, so when the failures occurs, what the software engineer or the tester will do is going to study those failures. Okay, is going to study those failures and is going to find the reasons for the failures. Why he is going to study the failures or the reasons for the failures? In order to avoid the failures that are going to occur in future. Understood? So engineers study the failures in order to understand, to prevent the similar failures which are going to be occur in the future. Understood? So that is the necessity of the fault based testing. Means whenever the faults or the failure occurs, we need to study that. Why we need to study that? In order to prevent the failures in the future. So experience with common software faults sometimes leads to the improvements in the design method and the programming languages. Suppose whenever you are using the programming languages, then the common software failure occurs or common software faults exist, and then we need to experience with those, because once you experience, or the developers once he experience with those failures, he can improve the programming language, or he can what he can do is he can design the new programming language so that the minimum or the number of failures can be reduced. So for example, if you consider in Java, the automatic memory management is used, right? So why it is required? So you have experienced the programming with C, you also experienced with the Java, right? You have done the programming using the Java, right? Yes, yes or no? You learned Java, right? Yes.
Yes, ma'am.
Suraj,
Yes, ma'am.
you learned Java, right? And what
Yes.
about Gaurav Kote? You learned Java, right? You learned C as well as Java, right? So when you're programming, which one you're feeling easier, C or Java? Tell me the answer.
Java, ma'am.
Suraj,
Java, ma'am.
Java is easier. Why? Yes, yes, tell me the
Um,
answer.
built-in classes are there, and
Yes, built-in classes are there, and it is a object-oriented programming language, right? What about C? C is a procedural level languages, and less number of built-in classes or functions are available in C when compared to Java. Since more number of built-in functions or built-in classes are available, you can directly use those classes in your programming, right? Yes or no?
yes, ma'am.
Yes, tell me. Yes. So, and one more feature of the Java is automatic memory management is also included in the Java. That was not there in the C. Is it yes or no?
Yes, ma'am. Yes, ma'am.
Yes. So then what is the advantage of using the automatic memory management? So whenever we are using the automatic memory management, yes.
Saves the memory, ma'am, in dynamic
It
allocation.
yes, it saves the memory as well as it avoids the failures or the errors whenever the users are writing the programs. See here, when if you are writing the program using C and when you're using the memory management there, then obviously it leads to the errors or the faults. Why? Because automatic memory management is not there in the C, right? And so it leads to the errors or the failure of the program. But since automatic memory management is included in the Java, it prevents the programmer from making the memory management errors. Means, so whenever automatic memory management is there in Java, so it prevents the programmer from making the kind of memory management errors. Understood? So memory management errors can be avoided whenever you're writing the program using Java language. So that is the advantage. So once you study the failures, and that failures can be avoided and new programming languages can be developed, or you can improve the existing programming language also. Okay, so this is the advantage of the fault analysis. So not all the program errors fall into the classes that can be prevented or statistically detected using the programming languages. So here, whenever we are testing the programs, then some statistical error occurs. So those statistical errors can be easily detected and can be solved by some of the programming languages, but not all the programming languages supports that. Okay, so it is we can't make it general. Okay, so detection of the errors or the faults and resolving those errors, that is once again the what we can say that it is depends on the program. Okay, it is a program the language dependent, we can say. It is language dependent, we cannot make it generalized. Okay, so this is about the introduction to fault based testing, why we have to go for fault based testing. So I'll come back to this slide afterwards. So first we'll start with the basic assumptions in the fault-based testing. Okay, so first we'll see if you want to perform the testing by using the fault model, then what are the basic assumptions we need to have. Okay, first we'll study that, then we'll go back to the this estimating the test suit quality and all. Okay, so first the basic assumptions in fault-based testing. So the effectiveness of the fault-based testing depends on the quality of the fault model. Okay, see here, the effectiveness of the fault-based testing methods depends on the quality of the fault model. Means whenever we are using the fault-based testing, we need to use the fault models, right? With these fault models, we are directly using in order to test the developed program or the system. So if we have developed the efficient fault model, then it is very easier to detect the faults or the errors. If the fault model is not efficient, then obviously the system fails or it is very difficult to identify or detect the faults. Hence, the effectiveness of the fault based testing methods depends on the quality of the fault model. So it will consider this quality of the fault model. Let us consider with the estimating the suit quality. So let us consider that I developed a program. Okay, I developed a program with bugs or with faults or with errors. Along with that, I'm going to add the new errors, 100 new errors into the developed program. So how I am adding? See here, I am having the real bugs in every way, and I make a copies of my program each with one of my 100 new bugs. Now let us consider one example. I have written the code for the commission problem, right? That I have already studied in the previous chapter, right? What is the commission problem and how the commission is going to be distributed to the salesperson depending on the sales quantity, right? That you already know. Let us consider the same example. I am having the commission problem. Okay, so that anyway, that commission problem consisting of some bugs, and along with that, I'm making the 100 copies of that program. Okay, I am having the original commission program, and I'm making the 100 copies of that program, and for each copy of the program I'm going to add 100 new bugs or 100 new errors. Then I will run that program to check the quality or the fault that exist in the program or errors exist in the program. So then how I'll do that? I run my test suite on the programs with seeded bugs. What it means, I am having the commission program, and I also developed the test case, and I have already added new 100 bugs to the commission problem. Clear? Or commission program. Then I'm going to run that program, where that program consisting of how many bugs? 100 bugs. Clear? I'm running or executing that program, and I'm testing that program by using the test suite or test cases. So whenever I'm executing that program by using the test cases, and some of the test reveals 20 of the bugs, some of the test reveals 20 of the bugs, the other 80 program copies do not fail. So what it indicates, even though you have added 100 bugs or 100 errors into the system, and when you into the program, and when you run that program, out of 100 program copies, only 20 program copies results in the error. After executing, it results in the error, and the remaining 80 programs will not fail, even though you have added the errors or the bugs into the program. And once you execute that, the 80 programs out of 90 programs will not give any error. Then what is the conclusion about this? So even though I added the bugs into the system, that bugs are not erroneous. Okay, those bugs are not erroneous, and hence they are not giving the errors. Understood? So this is the case. So out of 100 program copies, 20 program copies results in the errors, where other 80 programs do not fail, or they will not give the erroneous output. Why? Because even though we have added the bugs, those bugs are not erroneous one. Okay, hence they are giving the correct result, but 20 program copies are results in the errors. So that is the conclusion. Okay. Now, suppose that I have a program with bugs, add 100 new bugs, assume they are exactly like real bugs in every way. I make 100 copies of my program, each with one of my 100 bugs. Then run my test suite on the programs with the seeded bugs, and the test reveal 20 of the bugs, and the other 80 programs do not fail. Then what it indicates? Right, same thing I explained once again, right? What it indicates, as I said, the 20 of programs which are consisting of erroneous bugs results in the errors of the system, whereas the 100 other program copies, even though they consisting of the bugs or the errors, but those are not erroneous. This is the conclusion, or the that we can infer from the test suite's quality. Okay, so that we have considered here. So valid to the extent that the seeded bugs are representative of real bugs. So seeded bugs are means what? So seeded bugs are nothing but whenever we are adding the new bugs into the exist program, and those bugs are called as the seeded bugs. Is it clear? Understood? So real bugs are there. So this is the my program, right? I have a program with bugs. That is the original program with bugs. Whenever I add the new bugs, whenever I add 100 new bugs, what it indicates? It indicates that it is the seeded. Real bugs are nothing but the real programs with the bugs, and seeded bugs means whenever we are adding the new bugs into the developed program, such type of bugs are said to be seeded bugs. Okay, so when we are adding the seeded bugs, and these bugs are not necessarily identical. These are not identical. Means when it is not necessary that we are going to add the same type of bugs into the 100 copies of the programs. It is not necessary. For each copy of the program, we are going to add the bugs which are not identical, or we are going to add the bugs which are different from each other. Okay, for each different bug, we are going to add it into the program, and that is called as the seeded bug. Understood? Clear? Okay, so along with that, we are having the some terminology that you are going to study afterwards. And before that, once again, we are having some more assumptions. Competent programmer hypothesis means programs are not really nearly correct. So here, as I said, we have the programs and which consisting of the bugs. Then we say that the programs are nearly correct. Okay, some programs are even though consisting of the bugs, but they are giving the uh, results. Okay, real faults are small variations from the correct program. See here. So it is not really correct means we are having the real program which consisting of the faults, where these faults are small variation from the correct program. Now we have written the program for the commission problem, right? That is the correct program, but for that we are going to add the faults, and those are all the small variations from the correct program. Okay, then what happens? The error will not occur when we are executing such programs. Next, mutants are reasonable models of real buggy programs. We'll see in the next slide what are the mutants and other things when you're studying the fault-based terminology. Okay, so we'll see those things, mutants, in the next slide. Coupling effect hypothesis. So tests that find simple faults also find more complex faults. See here, we are having the two types of hypothesis. One is the competent programmer hypothesis. Second one is coupling effect hypothesis. So in the competent programmer hypothesis, we are considering the programs which are nearly correct, and in the coupling effect hypothesis, we are finding the faults in the developed programs, where those some faults are simple faults and some faults are complex faults. Even if mutants are not perfect representative of the real faults, a test showed that kills mutation is good at finding the real faults. We'll see the what are the mutants and all afterwards. So here we are basically concentrating on competent programmer hypothesis and coupling effect hypothesis. In the competent program, we are considering the programs which are nearly correct, and in the coupling effect hypothesis, we are performing the testing on the developed program in order to identify the faults. In such cases, we get the faults which some faults are very simple one and some faults are more complex one. So we'll see some of the terminology used in the fault-based testing. So first one is the original program. The program unit to be tested, and that program is called as the original program. As I said, the example, if you consider the commission problem and you written the program for the commission problem, and that program is treated as the original program. Understood? And the program location, a region in the source code, means where actually you stored that program, that gives the program location. Okay, so for example, when you are writing the C code, so how we are doing that? You are giving the path, right? C slash programming files slash DC slash your program. Then that gives the location for the program. Understood? Program location is the region or the place where actually you stored the source code or the original program. Next, alternate program. So alternate program is a program obtained from the original program by substituting an alternate expression for the text at some program location. Means we have the original program and we developed the alternate program of that. Then how will you differentiate the original program and the alternate program? In the alternate program, we are substituting an alternate expression for the text. Okay, at some program locations, right? You have written the series of lines of code. In the particular line of code, we are changing or substituting an alternate expression, and then it is said to be a alternate program. Next, distinct behavior of an alternate program R of test T. Here we are representing the alternate program R and the test as T. So here the distinct behavior of alternate program R of test T. Here the behavior of alternate program R is distinct from the behavior of the original program B for the test case T if R and P produces a different results, or if the output of R naught is defined for T, then we say that the distinct behavior of alternate program R of T. Now let us consider the original program as P and the alternate program as R, and we have the test case. We'll employ these test cases on the original program and also on the alternate program. If both the programs are giving the different results, okay, if both the programs are giving different results on the same test case or on the same test suite, then we say that the distinct behavior of an alternate program are of test T. Understood? Next one is distinguished set of alternate programs for a test suite T. Means a set of alternate programs are distinct if each alternate program in the test can be distinguished from the original program at least one test in T. See the difference. The distinct behavior of alternate program R of a test T. Here we are considering only one test case, and for the second case we are considering the set of test cases, and that results in a test suite. Clear? So now we'll consider the same thing. Okay. We have a original program and we have the alternate program, and we'll consider this case. Okay, distinct behavior of alternate program R of test T. For this we'll consider the original program P and the alternate program R. Then I'm employing this test case on the original program P and also on the original program and also on the alternate program R. If both the programs results in different, if both the programs gives the different results, understood? If both the programs gives the different results, then we say that distinct behavior of an alternate program are of test T. Next one is distinguished set of alternate programs for a test suite T. So what it indicates? Once again, we'll consider both the programs, original program and the alternate program, and the test suite consisting of set of test cases. Now let us consider that the test suite consisting of 5 test cases. If any one of the test case that we have employed on the original program and the alternate program, if that results in a different results, then we say that the distinguished set of alternate programs for a test suite T. Clear? Understood? So here in this one, we are considering it for the particular test case, but in the test suite we are having the set of test cases, and we'll consider the any one test case if it gives the different results for the original program and for the alternate program, then we say that the distinguished set of alternate programs for a test suite T. Understood? See the difference between the distinguished behavior of alternate program R of test T, and second one is same distinguished set of alternate programs. Here we have only one program, right? Distinguished behavior of an alternate program R, but here we are considering the set of alternate programs for a test suite. So here in this case we are considering a set of alternate programs, means we are considering 3 or more alternate programs along with the original program, and on those programs we are employing the different test cases. If they results in different answers, then we say that they are the distinguished set of alternate programs for a test suite T. Okay, so this is about the assumptions in the fault based testing. So what are the basic assumptions we have? So first we have to judge the effectiveness of the test suite in finding the real faults. By measuring how well it finds the seeded fake faults. So here we need to know what are the real bugs, fake faults, and the seeded bugs. Real bugs means the original program with a bug, which is called as the program with real bugs. Seeded bugs means whenever we are adding the new bugs to the copies of the program, then we say that it is a seeded bug. And the basic assumption here is the effectiveness of the fault based testing depends on the quality of the fault model and some basic assumptions uh, about the relation of the second faults. So that is basically we'll see that the basic assumption is the effectiveness of the fault based testing depends on the quality of the fault model. That is the basic thing we need to consider. And some of the terminologies that you have studied, one is the original program, second one is the program location, next one is the alternative program, and distinct behavior of alternate program R of test T, and distinguished set of alternate programs for a test suite T. So in the first case, we are considering a single alternate program. In the second case, we are considering the set of alternate programs for the test suite. Next, we'll go for the mutation analysis. So what is mutation? Then what a mutant is. So first we'll see what is a mutation. So mutation is nothing but the a program with a syntactic change is called as the mutation. So as I said, if we are having the original program with the bugs, if we are adding the new bugs, then it is said to be seeded bugs, right? Then the program with the seeded bugs is called as a mutation. Understood? So a mutation is a syntactic change. For example, see here, they are given initially if we return the program with the I is less than 0, and if we change that to I is less than or equal to 0, then what it indicates? It is a mutation, okay? Because here we have changed, there is a syntax change, right, in this. Or if you consider the example of in a for loop, if you're using the for I is equal to 0 to n and I plus plus, right? If that you are changing to I is equal to, for I is equal to n to 0, I minus minus, then there is a syntactic change there, and that is called as the mutation. Understood? Then what is a mutant? Mutant is a copy of a program with a mutation. So mutation means you have already changed or added the new bugs or added the seeded bug, and copy of that program is called as a mutant. Understood? Any doubt in the mutation and mutant? Yes, Misbah? Misbah? Suraj? Sharanya?
No, ma'am.
No, ma'am.
Yes, you know the difference between mutation and mutant?
Yes, ma'am.
Yes, ma'am.
Understood? See,
Yes,
mutation. What is a mutation? If you change, if you make any changes to the original program, then it is said to be a mutation. Okay. Then if you copy of that program, then that is said to be a mutant. Is it clear? Mutation and mutant. Mutation is a syntactic change, or when you change the syntax of a program, that results in a mutation. And if you copy of that program with a mutation, then it is said to be a mutant. Clear? Okay. Then we are running the test suite or the test case on all the mutant programs. Now we have the different copies of the mutant programs, and if we run the test suite on all the mutant programs, then we are going to get the different results. Okay. And a mutant is killed if it fails on at least one test case. Okay, a mutant is killed if it fails on at least one test case. So I'll explain the different test cases later. Right. After that, I'll explain that. Yeah. Right. So a mutation is killed if it fails on at least one test case, and if many mutants are killed, then infer that the test suite is also effective at finding the real bugs. So in the first case, we are considering the at least one test case is failed for the given mutant, then that mutant is failed. And like that, if many mutants are killed, then we'll infer that, or we'll come to the conclusion that whatever the test suite we used for testing the developed program is effective at finding the real bugs. So this is about the mutation analysis. So here, whenever we are performing the mutation testing, it uses the seeded faults or the syntactic mutations as black marbles. We will see other examples. So we will use the seeded faults or the syntactic mutations. I'll give the examples afterwards. And some of the terminology we are using the mutation analysis are these. Okay, first one is the original program under test. The original program is nothing but the program that you have developed. Okay, that is under test, is called as the original program. And the mutant is a program that differs from the original program for syntactic element. As I said here, in the condition, so for example, in the for loop, if I changed from I is less than 0 to I less than or equal to 0, then that becomes one mutant. Okay, so mutant is a program that differs from a original program. In the original program, I have written it as I is less than 0. But if I change that to I is less than or equal to 0, then that becomes the mutant. Understood? Clear? A mutant is a program that differs from a original program for syntactic element. For example, if we change the statements or the conditions or labels in the program, that results in a mutant. Next, we have different types of mutants. One is the distinguished mutant and other one is the equivalent mutant. So what is the distinguished mutant? A mutant that can be distinguished for the original program by executing at least one test case, then we say that it is the distinguished mutant. Means this mutant is distinguished from the original program, or it is different from the original program. How will you identify that? By executing the test case on the developed mutant. So if both are giving the different answers for that same test case, then we say that it is the distinguished mutant. Next one is equivalent mutant. If the mutant that can't be distinguished from the original, then we say that it is a equivalent mutant. Equivalent mutant is nothing but it is similar to the original program. Next we have the mutation operator. So what is a mutation operator? A mutation operator is a rule for producing a mutant program by syntactically modifying the original program. See here, as I already given the example, we are performing the syntactic changes. Okay, only we are changing the syntax of the program by using the mutation operator. So it is a rule for producing a mutant program by syntactically modifying the original program. So these are some of the terminologies used in the mutation analysis. Okay, one is the original program, second one is the mutant, and third one is the distinguished mutant, fourth one is the equivalent mutant, and fifth one is the mutation operator. Clear? We'll see some of the mutation operations or the mutation operators. So you know what are the mutation operators, right? We are allowing the these mutation operators allows to produce the mutant program by modifying the syntax of the program. Right. So syntactic change from legal program to legal program. So example is the specific to each programming language. If we consider C++ mutations don't work for Java, or Java mutations are not working for Python. Okay, here we have developed some of the mutations for C++. If you want to implement or include these in the Java programming language, then Java will not support the C++ mutations. Similarly, whatever the mutations we have for Java, that cannot be included in the Python program. So example is CRP. CRP indicates constant for constant replacement. For instance, from x less than 5 to x less than 12, select from constants found somewhere in program text. And next one is the ROR, relational operator replacement. For instance, we are replacing it to x is less than or equal to x is less than 5. So here we are changing from x is less than 5 to 12. Means here we are changing the values from 5 to 12. Right, but here we are changing the operator less than or equal to less than. So if we perform these type of syntax changes, then it results in a mutant, but it will not harm your program, or it will not result in any error. Okay, so next one is VIE, that is variable initialization elimination. Here we are changing from integer x is equal to 5 to integer x. Means we are not allocating any value or assigning any value to x. So then these are the sum of the operators we are using in the mutation operators, CRP, ROR, VIE, etc. Like that we have number of mutation operators for the C language. So each mutation operator is identified with the mutation ID, then the operator, description and the constraint. So CRP indicates constant for replacement. Okay, CRP is constant for a constant replacement. CRP is constant for constant replacement. Means what is the meaning of that? We are replacing the constant C1 with C2, where the constraint here is C1 should not be equal to C2. Similarly, SCR indicates the scalar from constant replacement. Sorry, scalar for constant replacement. Here we are replacing C with the scalar value x, and C and x should not be equal. Like that, we have the number of operators, mutation operators available in C language. So in the next class, we are going to study about the fault-based adequacy criteria. So far you have discussed about what are the faults, why do we require the fault-based testing, and what are the basic assumptions in the fault-based testing. Next, you have studied about the mutation analysis. In mutation analysis, you have studied about what is a mutation, what is mutant. Then you have studied about different terminologies in mutation analysis, like original program under test, mutant, distinguished mutant, equivalent mutant, and mutation operator, and what are the different mutation operators, list of mutation operators available for C language. So in the next class, you are going to study about fault-based adequacy criteria, and one more is the live mutant that we are going to study in the next class. Any doubt in this? Any doubt? Yes, Suraj, Gaurav, Sharanya.
No, ma'am.
Understood all of you?
Yes,
Understood? Okay. So you please study it. Textbook ಇದೆಯಲ್ಲ ಎಲ್ಲರ ಹತ್ರನು? All of you
Yes,
are
ma'am.
having the textbook, Xerox copy or textbook?